Good morning, everybody. Hope everybody's doing good this morning. We are halfway through the week, second week, so that's pretty good. And I was actually looking at the syllabus. We're pretty much on track, and almost we have a little bit extra time, so we'll just keep going. And then if we end before the semester ends, then we end before the semester ends. We can talk about other stuff or whatever. But yeah, I'm pretty happy about that. So today we are going to learn the other big important thing in programming, and that's going to be looping, iterations. But before we do, I'm actually going to kind of finish and where I left off last time, which was I was just kind of giving you a brief introduction into command line arguments, and I went through an example pretty fast, so I kind of want to go over it again for a little bit. And then I want to show you real fast Linux redirection, which is something that if it's not used now, it will be at some point in one of the assignments. Like, I'm pretty sure I used it. So I might as well just throw it in now so we can kind of get it out of the way. And then we can just kind of jump into looping. And then looping may take us 2 days. It might take us just the same day. I don't know. But I'd rather get those two things done first. So, okay. I guess without further ado, let's do it. Okay, so this is the same code from last time, and let me just refresh your mind on what's happening here. Of course, last time we mostly talked about formatting output and that kind of thing. So at the end, though, after we experimented a couple of things, I was talking about the concept of command line arguments, and as an example, I used the program in Linux called head that prints out the first few lines or characters of a file, of a text file, right? And if you don't remember, I can refresh it. You just type, well, if you just type in head, nothing happens because it's expecting actually input. But if I go and type in head and then put the name of the file, so like maybe tax.cpp, it's going to print out the first, I think we said 11 lines, but let's see, 2, 4, 6, 8, 10 lines. Okay, so 10 lines of the file. Now, technically, we are giving it one command line argument, and that's the word of the name of the file that we are working with, that we want to print out. But we can give it more than one command line argument. In order to find out which command line arguments it takes, most programs allow you to give another command. Oh, I see no connection. You guys there? Let me write something on the chat because I see no upload speed. Is reader running? Disconnected, reconnecting. Yeah, I think we're having some technical issues. Yes. See, it shows down here red for me, 0 kilobits per second. For my upload, which is a sign that I'm not, yeah, it just shut down the stream. So, oof, okay, we'll just wait. Let's just wait a few. At least it happened in the beginning. So, if you're watching on YouTube, feel free to just fast forward, I suppose, through this time. Reconnecting successful. Okay, so it's coming back. Okay, cool. Yeah, so we are fully back. So hey, at least that happened in the beginning and not in the middle of a topic, so that's good. Yeah, so I'm glad I caught that early on. So, okay. So anyways, I don't know where it cut off, but I'll just start what I was saying with the head. So the head will print out the first 10 lines of a program. And if you want to find out more about how that program works, there's another command line argument that you can use, and that is called help. And it's sort of a standard that somehow somebody kind of decided, and everybody was just like, yeah, it's a good idea, we'll follow it. Where you put these dashes in front of your command line arguments, and you have two versions usually. One of them with a single dash is like an abbreviated format, And then with 2 dashes, it's sort of like the verbose version of that. The example of that being here, as you can see, some of these, like -C, can be written in a verbose way by writing this whole massive thing right here. Same with the lines one, you can do -N, or you can do this -- lines. This version is a little bit more sort of descriptive of what you're doing. This is the shorthand for when you're trying to, save some time. So yeah, so like an example of that is I can do -head -N, and then maybe 3 lines, and then the name of the file, which is tax.cpp, and you can see they're just the first 3 lines, which are the preprocessor directives. I can also do -C, and that one is a number of characters. So if I say 5 characters, it should say like incl. Yeah, incl right there, because that's just the first 5 characters. Of course, I can do like 50, and that's almost the first 3 lines. Let's do like 5,000. That is more than the size of the file, so you just print out the entire file and pretty much ends there. So anyways, that's how command-line arguments work. And of course, we want to do that in C++ because it's useful if you're running some sort of script. You can feed in the right command-line arguments, and also your program can work on them. So in our example, what we had was, run it. We had the net income and the gross income, and we wanted to create a command-line argument that decided how many digits after the period, so how many decimal digits we wanted to have in our program. However, we also want to kind of have a default, and the default is that it has no digits, right? And so if we don't put any command argument like this, other than the file name, I suppose, then it just kind of defaults to just no decimals. However, I can go ahead and put a 2 there, and it now defaults to having 2 decimals. If I go ahead and try 8, you can see there that it puts a bunch of them. Obviously, the second one is exactly 0.5, I suppose. Or actually, it's 0.49999, I think, but that rounds it up to 0.5 at that digit. However, if I just did 1, I think it would stay at, actually, I think it'll go 5, yeah. It's only when I do 0 that it rounds down because it's 0.49. So, yeah, or I not just do anything because the default is 0. So the way that we actually implemented that is you use parameters in your main function. So before in other programs, when you're writing main, you just hit in main, open parentheses, and clone parentheses, right? Well, now we're sort of using these parameters for something. And it happens to be the default is that in main, you have an integer and a character array. We haven't talked about arrays yet. We will at some point. But what they represent is this integer is the number of arguments given. And at the very least, when you run ./a.out without anything, like this, that's 1 command argument. So argc would have the value of 1. However, if you go ahead and you run this with more than 1 command line argument, so maybe you do like that, then technically this is 1, 2, 3, 4 command line arguments, okay? And so that is what that value is going to hold. The second one is that's the one that's a little bit complicated. That's an array, and what array is, and again, we will talk in detail one of those days when we get to that, is it's a list. It's a list of these arguments. So it basically stores each of these, so it stores this in a list, and it just puts them in a little table. And the first entry of the table is going to be a.out. The second entry is going to be this one. The third one's going to be this one, and the fourth one's this one. And so it kind of puts them in the little table nicely. Like think of like an Excel spreadsheet, little table like that. And in fact, I can even, let's just to make sure we're clear on that. You can think of it like this. It's a little table like this, and it puts the arguments in this order. So let's go ahead and try something more interesting than just the a.out. So maybe we do like a.out high, or here, 11, high, and then hello, like that, okay? So if this is what you're doing, what that little table is going to look like is going to be a.out in that first entry, 11 in the second one, high on the third one, and then hello on the fourth. And that's pretty much it. Okay? And so argc actually stands for argument count. And that's the number of these that we have. So we have 4 entries here. So argc would be equal to 4. argv, on the other hand, which is the second one, so when you have int main, you have int argc, comma, car to asterisk, which we haven't talked about what they mean, argb like this, okay? By the way, these names, argb and argc, they can be anything. I could actually change them, but it's not a good practice because that's just kind of the standard. But I could name them A and B. It's just kind of weird to do that, so I would leave them be like that. But anyways, argv, that's a debatable on what it actually stands for, but I believe it's argument vector, or yeah, I suppose so. But you can just think of it as the actual arguments that you're passed in, okay? And while we haven't really talked about arrays, these square brackets when you're working with an array actually are used to indicate which of these rows you want in that array. And so if I put a number 2 here, that's going to give me this well, this is a little tricky. It's actually going to give me the third item, so it actually would give me the high. But that's because you start counting from 0. So normally in math, you say this is the first number, this is the second number, this is the third number, this is the fourth number, right? Well, in C++, it actually turns out that you start counting from 0. So this is actually 0, 1, 2, 3. So the example that I like to give with the whole counting from 0 versus 1 is, think of like a parking lot or a parking garage, actually, because that has to be a multi-story parking lot, okay? In the US, you know, when you got a little parking structure like the ones we have at UNLV and so on, we have level 1 here, then we have level 2, level 3, level 4, and level 5 of like Cottage Grove, right? This is the base level, right? This is where the street is. We call that level 1. And then technically the first walk of steps you would do here would take you to the second floor, right? So like in a 2-story house, you live in the first, you know, your entrance is on the first floor and maybe your bedroom is in the second floor, right? That's how we do it in America. But if you go to Europe or some other places, they do a little bit different how they count the floors. They have sort of like the bottom floor, which they can call lobby or something like that. And then actually what we would consider the second floor, they call the first floor. And so they kind of shift their flooring scheme because of that, because they have sort of the base level, and then what they call first floor is actually what we call the second floor, because it's the second, like it's like one up. But in a way, you can think of like their bottom floor as a 0, like level 0. Like some elevators in Europe have a 0 on them, and that actually stands for like the bottom floor. Whereas in America, if you see a 0, it might actually be a basement, like underground, but not in Europe. In Europe, 0 is actually like street level. Okay, so you can kind of think of this example of counting from 0 in how actually arrays work. They start counting from 0. So when you see a 2 here, you're looking at it in like the European system, which would be here, which means there's actually the third sort of parkable area that you can do, versus in America where it would be the second, okay? So just remember that sort of metaphor or a simile to how arrays are kept. And I'll bring it up again when we start talking about arrays. But anyways, basically that's what this means here. That means that you access the high. If you wanted to access the 11, you would do argb 1. If you want to access the a.out, you'd actually just do argb 0 here. And this will give you access to these things, okay? And so, again, we'll come back to that in more detail when we talk about arrays. But for now, what you're seeing in this if statement is I am checking to see how many arguments the user passes. And only in the case where argc is equal to 2, which means he passed 2 arguments, which means a.out and then a number, only then am I going to assume that that second argument is actually the number of decimal digits he wants to pass. If he passed 1 argument, such as the ./a.out, it means that he didn't pass a number for the number of digits. So I'm just going to stick with my default, which is 0, which is what I initialized this to. If he passes 3, it means that he's passing some weird stuff he shouldn't. So in this case, I'm just going to ignore everything because it's probably wrong and just again stick to 0. This is strictly something that I chose to do, but you could choose to do something completely different. However, here's the thing. Imagine that you are in the parking lot here. I guess we're in the European one, so we're on this one. And suppose there's a little elevator here, okay? And you get on the elevator and you press button 2 there, okay? So that means it's gonna take you here, right? And then the doors open and you're good. Okay, suppose that you push button 8 in this elevator. Like somebody gets in here after you get out and they push an 8. And for some reason the elevator has 8 buttons, but there's only technically 4 floors, right? It goes from 0 to 3. What's gonna happen then? Well, elevator is gonna go up, it's gonna go up, and then it's gonna run out of places to go, and then it's gonna crash down, and it's going to make like a big explosion. Bam! You know, get the fire department in there, and hopefully the guy had a parachute or something, so he survives. But you know, no people were harmed in the making of that example. But ultimately, that's kind of what happens when you try to access something that doesn't exist. So in our ARGBs here, there's only 4 spots, which are indexed from 0 to 3. If I try to access something that doesn't exist down here, then I'm accessing the void, like nothing. And lots of scary things can happen when I access the void in computers. That means I'm accessing memory that I may not have access to, or that it contains garbage. And ultimately, in the best case scenario, you're going to get random garbage, which is not what you intended. And in the worst and most common scenario, your program is going to crash. And what does a program crash look like? That's when your program freezes and then it just closes itself. And sometimes it gives you an error saying, this program has crashed, please would you like us to send a report to the developers or things like that. And that's useful to the developers because your program's not supposed to crash, right? But when it does crash, it copies a lot of information about the state of the program, what you were trying to do, like what the computer it's running is like. So are you running on Windows? Are you running on an iPhone? Are you running on an Android phone? Are you running on a Mac? Where were you running your program? What were you doing in the program? Copy some of the personal information that you may have been doing in the program, and then packs everything up along with some variables inside of this that keep track of sort of the state of what was happening, and then it sends it all via internet to the developer, for the better or the worst, because there may be personally identifiable information in that package depending on what the contract says when you run a program for the first time and you hit accept on the terms without reading them probably. So beware of that, I suppose. So anyways, basically that's sort of the big program crashing situation where it just freezes. In our scenario, in something like CS135, programs crashes are a little bit less fancy than that. And to show you, I'm going to go ahead and turn off the check that I have for the argument count. And then I'm going to run the program again, but I'm not going to give it any arguments, which means I'm going to be trying to access that second argument in a parking lot that has no first floor in the British style, which means there's nothing. There's literally just flat land, and I'm trying to access the floor above the flat land. So, of course, it's going to crash. Well, I got to compile it first. And you can see here that it says segmentation fault core dumped, which we saw last time too. And so this means that the program has crashed, essentially. This is Linux's way of saying this program has crashed. The core dump part means that as part of the crash, it, like I said, it saves some of the information from the program and saves it in this special spot in memory that keeps a copy. Oh, yeah, sorry, my bad. Yeah, so I went ahead and just simply ran the program, and I run it, and you can see that it says segmentation fault. Okay, so this means that the program crashed, and also it saved a copy of some of the program's information, some of the variables and other things, into a special file. And the idea is that file can give you some hints, if you have the right tools, to try to explore as to the reason why it crashed so that you can fix it. That's beyond the scope of this class to be able to look at that file. However, if you see that, it means your program crashed. And you may see stuff before the program crashes, like if you're printing output and then it crashes, you may not. That's why some people like to debug using print statements so they can keep track of variables before something crashes. But anyways, now you know what segmentation fault core dump actually means, okay? We of course don't like seeing that, but If you do, it means something is wrong with your program, like very wrong with your program. Obviously, the fact that you were able to compile it means that there's no syntax errors, and this is strictly a semantics error. So, okay, and I'm just gonna go ahead and re-add in my if statement, because that if statement is meant to be there to check. It's like literally the elevator checking if such a floor exists before moving there. Of course, I only know that floor exists because I have the argc variable that tells me. If I didn't have that, there would be no way for me to actually find out if a floor exists or not until I actually get there, which is a very dangerous thing to do. And yet again, when we get to arrays, we'll talk about how to keep the size of such an array, or how to keep the size of the tables. But anyways, as I said, we have it set now so that the second digit is going to go ahead, which says argv1 here, is the decimals. So now, here's the thing though. In our little table that has all the arguments, right here, these values are kept as characters. They're not kept as integers. So like, this is a string right here. It's a C string technically. However, the 11 here is not a number 11. It's 2 1s in ASCII table representation, okay? So in the ASCII table, the 1, I don't remember what it is, but let's just say it's 41. Like literally the ASCII value of 41. That is if you're trying to manipulate that character, it's not a number, and the computer doesn't understand it's a number. It just looks like a number to you, but it's not a number. And so one of the ways that you can work with that is you can convert it to a number by using a function. And in this case, we used a function in the cstdlib header file, which is a C header file, I believe. And we used a function called a2i, which means alpha to integer or integral. And what it does is it converts an alphanumeric character into an integer, which is exactly what we're trying to do. And so what this function requires is the character representing what you're trying to convert. So if I feed it here the character of like 1 with single quotes instead of this, then it will do the same thing. And so this function is going to return me the actual number representation of that. So here I am taking the 2 because I ran that as a 2 here, but it's converting that car of 2 into the actual number 2. And you could do this yourself by hand, actually. You know how to do this with what I've taught you so far. Because what you would do is you could use an if statement to compare the ASCII value there to what your ASCII table has. So in your ASCII table, let's actually really fast, let me go ahead and look that up. ASCII table. So here's our ASCII table, and the 1 is right there. It's 49. I was close. I said 41, but it's 49, so not bad. So because the ASCII representation of 1 is 49 and 2 is 50, what you can do is you can do an if statement comparing the argv1. You can compare that value, at least the first spot of that string, you can compare that number with 50. Is that car equal to 50? Or you can simply say compare it to another car that has the value of 1 in it. And if they're equal, then you know that it stands for a 1 or it stands for a 2, and then you can actually go ahead and convert it by hand. It's a good exercise that you can do. I don't think I have anything like that in the assignments, but you can probably definitely do it on your own. So you can definitely create your own sort of equivalent to this. But of course, you know, it's so much easier to just use the ones that are given to you, especially when I'm trying to go over this, because I don't want to spend an hour writing this for every single number and also combinations of numbers and things like that. So anyways, that's what's happening here, and that's how this works. That's in general how command-line arguments work. Again, we'll revisit them when we talk about arrays in detail, which is quite later on, maybe in a week and a half from now. Okay, so that covers the command-line argument segment. So I'm going to go ahead and close this now. Next, I'm going to talk to you about Linux redirection. Okay, so let me write that down here. Actually, for that, I might want to use the iPad for a little bit. Let me know if there's any questions, by the way. So, what is Linux redirection? It's actually a rather simple concept, but I tend to notice that, like when people get to 202, or even 302, they don't know what this is, and they're so confused. And I'm like, why? You know, you could have literally taken 5 minutes in 135, like whoever thought it, and just cover this and move on with your lives. So that's why I want to make sure that I cover it, because it's very, very useful. So right now, when you're running a program, so if I have a little program that is supposed to say, that asks the user for their name. So here, let me write real fast a program that asks the user for their name and then tells them hello by their name. So hi, what's your name? And then we got to store that somewhere. So we're going to store in a variable called name. So let me declare such a variable, string name, cin name, and then it says, nice to meet you, comma, and then name. Like that, okay? And so if we run this now, oh, not tax, let me go to the folder where I created that file. Expected, I forgot a semicolon right there. In fact, yeah, like that, that's fine. Okay. What else am I forgetting? Oh, I put a colon instead of a semicolon. There we go. Okay, so it asks me, hi, what is your name? So I can say my name is Doc. Nice to meet you, Doc. Maybe I should want to put a period afterwards, or an exclamation point, and then maybe a smiley face. Okay, let's give that a try now. Nice to meet you, Doc. Okay, cool. So as you can see, the program is interactive. It requests input from the user, and then it actually outputs to the terminal some messages as well. Okay, so cin is going to take that default input from the terminal, and cout is going to take the default output to the terminal. Okay, and so Linux redirection allows you in general for Linux, and this works also for Windows and whatnot. It might be a different character, but I believe it's the same ones. What if instead of you typing by hand input, you want to redirect it from a file that you create ahead of time? What that means is that every time that I run this program right here, you know, if I go ahead and say a.out, it's going to ask me, what is your name? And then I have to type it in by hand by saying Doc. And I will press enter, and then the program processes that input and then returns to me a message, which is an echo of you know, we talk about echo printing in a way, because it's just printing out the same thing I gave it in, and just wrapped in different text. So sometimes it's convenient to feed information into your program that is pre-written ahead of time, especially if your program is supposed to compute a bunch of taxes and you have to manually enter the tax information. But you could create a file that's going to enter it ahead of time. And that's what Linux redirection is going to basically do. It's going to, you know, your program usually takes input in the form of cin to your program, and then it outputs it using cout. And here's your terminal. Actually, I suppose a better way of representing this would be like this. So you got your terminal here, and you got your program here. Okay, and so information coming in from the terminal is called cin. Information coming out is cout. And typically it's a cycle, right? Because you ask for information, you receive information, you ask for more, you receive, and so on until your program ends. Okay, and so this sort of cycle is very convenient, but at the same time, you as a user have to manually enter information here, and also you have to manually read it. So I suppose the better example could be, what if you want a copy of the information that gets printed? What if you want to store that on a file for later review? Or on the side of the cin, instead of writing doc every time, what if I just want to create a file that has my name, and then I can just use that file to feed it in? Of course, here is just one name and you're like, that's so much effort. But suppose that my program required like 20 different inputs, each input representing, actually think about the assignment 3, the quiz. You know, for your quiz, your program asks you a series of like 6 questions, and then it finally outputs the score or whatever you're accepted or not into the club. So suppose you go out on the streets and you ask a bunch of people these questions and you write them down, their answers for each person. And so you create a file with each answer for each person. So one file contains all answers from one person. And so now you want to feed it into your program so it processes and gives you back the output. And so that's essentially what Linux redirection is very useful for. It allows me to replace me manually entering input into the terminal, and instead, the input is read from a given file. And on the other side, I can do the same thing by saying, instead of having to like read the answers on the screen, and then if I want to back them up, I could like, you know, I could highlight this and copy and paste it into a file. I want it to automatically be saved to a file, sort of like a log file, okay? And the way you do that is very, very simple. It's just a matter of basically using the less than sign or the greater than sign. So if you have a file, or like an executable that is a.out, and you want to save all the output from that into a file so that it's no longer printed on the terminal, but instead it's printed into a file, you're going to use that sign, and then you're going to put a name of a file. So like output.txt. Beware, if such a file already exists, it's going to overwrite it. So I've seen people put the name of their programs right here. So like, let's say hello.cpp, and then they run it, and then their entire program just got overwritten by output, and bam, they just lost all their work if they didn't have a backup. So be careful about that. So anyways, that is how if you do that, it's going to take any output that would have gone to the terminal and it's going to redirect it. So in a way, what it's going to do is it's going to kind of cut this link away, and instead it's going to redirect it, hence the name Linux redirection, into a file called output.txt, because that's the file that I gave it, okay? On the other hand, you can do the same thing for the input. So we'll call this Linux output redirection. For the input, you can do the same thing. You can do a.out, but then instead you can use that less than and then give it a file name. So I guess it makes sense to call this one input.txt. Same thing here. In this case, it's going to cut off this link and it's going to replace it with a file called input.txt. So anytime your program requests information, it's going to pull it from that file, and it's going to keep sort of a cursor to where it's been on the file so that it just keeps going and it doesn't start. Every time you do C, it doesn't start from the beginning. Okay? You can, of course, combine both of them and do both in and out from files. So they're not necessarily exclusive that you can do one or the other. You can do a combination of both. The way you do that is you just literally put both side by side. And in this case now we're doing both the input and the output, okay? And now the terminal is not involved at all, actually. Now you just execute your program and that's it. You won't even see anything happen on the terminal. So let's go ahead and actually do that. Let's first do the one for the output, because I want to show you something that will happen. So when right now I do a.out, I can put doc. Oh, hold on, let me switch it over so you can see. So right now I do a.out, and it asks me for my name, and I can put it in. But now I'm going to do a.out, the little greater than sign. I'm going to put like output file.txt. And I run it, and notice that it's not asking me for a prompt. However, I still got to type it in by hand, press enter, and again, it doesn't say nice to meet you or anything. You're like, where did that go? It's there. It just happens to be in the file. So if we go ahead and type in ls, we can see now that there is a file called output file.txt. And if we go ahead and use, let's use the head command, why not? Head output.file.txt, you can see that in there it says, hi, what's your name? Nice to meet you, doc. Notice that there's no doc in here. as it would have been here where it echoes. It just printed out the prompt and then the answer to the prompt, and you don't see any of the input. So it's strictly redirecting the output stuff into the output file, none of the input that you type in. Nope, it's not laggy right now, but I would suggest you refresh. It might be your internet. Check your internet, run speedtest.net. Speedtest.net like that, and see how you're doing. You could also try lowering the resolution of the stream, or turn on buffering, which will add a delay to it, but it might help you. So just give it a try. If not, then you can always check out the YouTube video later. So yeah, but the refresh and lowering resolution is probably your best bet. But anyways, let's go ahead and remove output.file.txt. As you can see, it's gone, so you don't see there's any tricks going on, And then I can do a.out again. And this time I'm going to do, oh, shoot, I forgot to actually do the output file.txt. Now I'm going to say my name is Padme. It's my dog. And so now if I go ahead and do head output, you can see, hi, what's your name? Nice to meet you, Padme. Okay? All right, let's go ahead and let's not remove it this time. Let's just keep it there, but I'm going to show you how it overwrites. In this case, let's combine input and output. So first we need to make an input file. So let's go ahead and use nano and say input or in.txt. And all I'm going to do in there is I'm going to write a name. So in there, I'm going to put the name Padme Kira, or actually I can do multi-words. So I'll put doc again, doc.js, because I have Padme. So I want to show you how it overwrites. Okay, so now I can go ahead and say cat, or also use head since we're in the head mode right now. Oh, typo. We can see that we have a file with just doc.js in it. That's all that's in that file. Okay, there's nothing else. It's a text file, but I do have an enter at the end, which is kind of important because you got to press enter to read input. So yeah, okay. So now let's go ahead and run our program. .slashes are out, but instead let's use that one, the lesson sign, and then let's go ahead and put it in .txt. We're not going to do the output. We're just going to do that. In this case, it's kind of the opposite. It says, hi, what's your name? But it didn't ask me for me to type anything in. Instead, it read it in directly from the file. And then it said, nice to meet you, doc.js. So in this case, instead of me again, let me show you what it is again without anything. Here, I would have to manually type in my name, blah, 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 blah. And then, of course, it would say the same thing with the name. But in the other one, here, it doesn't require me to do anything. So like, for example, your TA, when he's grading, like assignment 3, he doesn't have the time to manually press yes or no in multiple combinations to test your assignment. He can just prepare an input file with a combination of answers he wants to check. So maybe he wants to check a positive response, a negative response, and a perfect response. And then he can just feed it in using this method. Furthermore, he can also combine them, the in and out, by going ahead and doing like output file.txt. Press that, and in this case, you don't see anything happen. You're just like, the next line happens. However, if I go in there and I look at output file.txt, remember I had Padme before, but now it has doc.js because that's what the input gave it. So in this case, it overwrote it. So be careful though, that's the one thing. It will overwrite the file that you're working with. There are ways to append instead of overwrite. You can go ahead and read more about Linux redirection in your own, because there's a lot of different things you can do, such as if you want to both print out the text to the terminal and to the file, you can do that. You can also, as I said, append, which means instead of every time you overwrite to the file, you can just sort of add to the end. That could be useful if you're just trying to make one file with all the responses, like a big logbook. But most of the time, you probably just want to replace the file so that you have a clean slate. So yeah, this is definitely something useful. And I guess while I'm at it, one of the things that, okay, so right now, I'm going to go ahead and rename the output file into, like, let's say, solution.txt, okay? So let's go ahead and rerun the program again. But this time, let's make a little typo here. Let's say I put an uppercase U, like that, okay? And so now I'm going to recompile it. What is it called? Linux redirection? And then I'm going to run it again using the Linux redirection. So I'm going to still use my in file, which should give me the same name. And then I'm going to put it in a file. And then I'll call this one student output.txt. I run it. I can go ahead and look at it. You can see that there's that file and the solution is there as well. So the solution will use the head just because I like using different things. And they look the same, right? But the TA doesn't want to do this probably. He doesn't want to have to like visually look at them. So one of the things he can do is he can use a little command in Linux called diff. And with diff, I can put both the student solution and the real solution side by side. And in this case, if the solutions are not exact to the dot, then it's going to show them like this by showing both columns, the one from your answer and the one from my answer. So obviously he sees this and now he actually has to take the time and look and see what's wrong. And then he says, oh, you know, there's an uppercase Y, right? You can also put them side by side. I think by doing that. Yeah, but then it looks kind of weird here because it's really wide, but it would put them side by side if it was a little bit shorter. I can try to expand this so you can kind of see that, but you can kind of see them side by side. And if they weren't, then it would skip that line entirely. Let me bring that back. I guess it was around there. So anyways, that's very useful for grading. And now let me go ahead and fix that by making the input exactly the same. And now let's go ahead and recompile, rerun it into the student output. Now let's run diff again. Notice that there's no output, nothing. It just prints out blank. If I do the other diff, it does print it, but there's no line. There's no vertical line. But more importantly, the reason why there's no output here is because there's no differences between them. It means that they are perfectly the same. And so if your TA is grading, and that's why I insist you should match your output to the dot, including if there's errors like typos in my output, in my sample output, then you should put those typos in your output, because then the diff will not show any differences, and your TA will still go and look at the code to make sure you didn't just hard code stuff. But it makes grading a lot faster because he can just run a diff and see the differences. Now, of course, he doesn't have to do this. He can do his own thing. But at least the one time that I was grading stuff, one time I was a TA for one summer class, actually 202. I did this method and it sped my grading up way faster. Because the only times that I had to look at code was when the differences were like this. And also you can do some tweaks to it skips white space. So if there's like a space, it's okay. It only looks, and they can also lowercase everything to remove things. So yeah, it can work for very complicated stuff where there's a lot of numbers that you gotta compare and things like that. So anyways, that's a diff is quite a useful feature that you can use in general. So if you copy my output file, like if you look at the PDF at the end where I have sample output, if you copy that into a text file and then you do the diff with the Linux redirection, you yourself can grade and check to see if there's any typos and go ahead and fix that up. Yes, you do lose points if your output differs from mine or from the norm per se. You will indeed lose points. So that's why I'm taking the time to kind of spiel about diff in general. So anyways, that's Linux redirection for you, and that's one very good use of it, which is grading. But in general, I use it all the time when I'm running a script or something, and I just want to log it to a file. That way, if something happens, the file has a copy of it. If the computer crashes and shuts down, you know, if it was just on the terminal and I never got around to actually looking at the terminal, it's gone forever. But at least in the file, it's going to be saved. So it's a very convenient thing to do. And some assignments require it because it's a way to feed it a lot of data. So yes. What about the DAR thing? Because I kind of smushed it to get 74 column requirements. As long as it matches my output, it's okay. And that's sort of priority one. And then priority two is, of course, following the syllabus stuff. So if some of my output was not up to standard with the 74 characters, that's okay, as long as mine wasn't like that already in the sample output. But if in my sample output it was like 60 characters and yours is like 100, then that's where you're deviating from that. So yes. And like I said, there are fancier ways to get rid of some of the spacing stuff, so it doesn't always just completely give you warnings for like an extra space or things like that. And it actually gives you warnings for when things are actually different, like real numbers are different and things like that. So, okay. So I'm glad I took the time to go over that. So now we can move on to talking about loops. Iterative code, as it's called. And by the way, if you redeem the extra credit, which I do see a couple of people did, make sure you tell me who you are on Discord, even if you have told me before. That way I can add you in. I had someone yesterday redeem the extra credit, and I don't know who they are. So like, I'm just kind of waiting to hear from them. So otherwise, I don't know. Like, you guys got some obscure names, you know, so I gotta know. Otherwise, I don't know who to give the points to. So they're just, I mean, you're not gonna lose them. But you know, they're there. It's just one person that didn't. You did yesterday. No, you're the person that you didn't tell me who you were. I didn't get a Discord message from you. So send me another message, because I didn't get it. So yes, you are indeed the person, because I'm looking at the chat here. How can I get extra credit? Attendance. So yes. Well, that's fine. That's fine. But now you do. So make sure you you let me know who you are. That way I can give you the points. Because like, I don't know who Moesa Zero is. Like, some of you have names that are kind of hint what it is, but I don't want to give it to the wrong person. So it's okay. Just, you're not going to lose the points. Just at some point let me know, and then I can actually go in and give them to you. So it doesn't have to be now, but just make sure you do it. Otherwise, do it before the end of the semester. So, and do it on Discord. Don't do it here, because then their name is public to everybody, and that's kind of weird. You just DM me. Nope, I did not get a DM on Discord. So make sure you're DMing me on Discord. Don't do it on Twitch. I don't know. You might have done it on Twitch. I have no idea. So, anyways, okay. So loops, big topic of the day, and probably gonna flow into tomorrow. Okay. So right now, you learn if statements, which is very important to be able to have your code branch into different sort of possibilities, different universes, and so on. And then you've also done code that always just runs from beginning to end, and that's it. There's no deviation, okay? However, for example, with assignment 3, you got yourself a calculator, and the calculator runs once, and then it just stops at the end, and then you got to rerun the program to run it again. Same with the quiz. The quiz runs once, and then you're done. There's no way to go back and do both the quiz with the calculator or run the quiz multiple times. So what if you want your program to run more than once and sort of continue running? That is where the concept of looping comes into play. So your programs right now, they go like this, or if there's like a decision, then, sometimes they go like this, and other times they might go like this, and other times they just go like that. I guess one or the other, right? So what we want to be able to do is we want to be able to run the program and then go back to the top, run it again, go back to the top, and run it as many times as the user wants before terminating. If it's something with like a decision tree, with an if statement, in this sort of situation, maybe the program's going to run one time like this, but then we want it to loop again. And the second time it might run this way, and then loop again, and then maybe it'll run this way, and then loop again, and then maybe it'll run this way again, and maybe loop again, and maybe this time it'll run this way, and so on. And you just keep doing that repeatedly until at some point, you just end the program, okay? So that's really what we're going to be covering today. The idea of being able to loop around your program. Furthermore, for certain computations, you need to do something repeatedly. So for example, let's say you're trying to implement a piece of code that can compute the exponents of something. So if I say 2 to the 5th power, how do we do that? Right now, you know how to do it using the pow function. Yeah, sure, you can do 2, 5, right? But what if you want to implement it yourself, like with your bare hands, no function calls, okay? Well, the way you can implement this in a program, if I was trying to teach somebody, somebody asked me, like, they have no idea how exponents work. They don't even know why that number isn't up there and smaller. how would you as a person explain to them how an exponent works? They know multiplication, and they know subtraction and division. They just don't know exponents. Well, what you tell them is that the number there signifies that you're going to multiply this number here, which is we call the base, and you're going to multiply it by itself this number of times, which in this case is 5 times. So this can be rewritten into 2 times 2 times 2 times 2 times 2. This is the same thing as saying 2 to the 5th, just like it's, you know, if you had something like 3 to the 3rd power, or maybe second power, it's just 3 times 3. If you have 4 to the 3rd power, that just means 4 times 4 times 4, okay? So that's how you explain it. So really, if you're trying to program this, what you need to do is you need to write code that multiplies something by itself the number of times that it's in the exponent. But see, that is sort of a repetitive function that you have to do, and that is not just repetitive, but it's dependent on the number here. Because yeah, in this one you got to repeat the multiplication 5 times, but this one you only repeat it twice. This one you repeat it 3 times. So it's something that's variable. If it was always 5 times, you know, if A contained that value, I could do something like A equals A times A, and then I could do the same thing by saying, or I suppose you could do maybe A times 2, and then again times 2, and then A times 2, and then A times 2, and then finally A times 2. And then if I wanted to do the second one, then all I need is these 2 lines here, except this has to become a, what is it, 3? And you have to initialize it, right? So it's going to depend on what these values are. And so that is the idea of looping. We wanted to be able to have 2 major kinds of loops. One of them that is count based, so you loop a certain number of times that you define ahead of time. And the other kind of looping is event based looping. And that's the kind of looping where you're going to loop until something happens. And you don't know when that's going to happen. It could happen the first time you loop around. It could happen in 100 times. But hopefully it happens at some point so you don't just go forever. That's a whole nother problem. So that's event-based looping, and then we also have counting-based looping. So let's go ahead and start with event-based looping. So let's go ahead and do event-based loops, okay? And for that, there are 2 of them, but first we're going to cover 3 loops. So make sure you remember to cover 3, I suppose. But the first one is going to be while, which is going to be the primary one for event-based looping. And it's called a while loop. Okay, a while loop looks kind of like an if statement. While is, of course, a reserved word. So you would write the word while. And then you're going to put in here some sort of logical expressions, just like the if statement. And then you're going to put your curly brackets. And of course, scoping rules come into play because of the curly brackets. And then when you finish the code that's looping, you're going to put another curly bracket. And then of course you have some code down here and you have some code up here, but that doesn't matter. In here, you're going to have a sequence of statements. Or other things. You could have another loop inside if you want. You know, that's called nested looping, just like you have nested if statements, okay? This logical expression, though, is kind of going to work like the if statement. Because if you recall with the if statement, you enter the if statement if the logical expression evaluates to true. The same can be said of the loop. If the logical expression evaluates to true, then you enter the loop. But with the if statement, when you finish running the body of the if statement here, where the statements are, at the end of it, it finishes and it just keeps going, right? Well, that's where the while loop is going to deviate from an if statement. In that case, when it sees a curly bracket here, it's actually going to go back to the beginning of the while loop. So it's going to take the sort of, if you think of like a little line pointing to what code is being executed, it's basically gonna start here. If I can draw an arrow, close enough. So it starts there. Then it goes down to this, runs code there, any code, finally hits this thing, and then it goes back to here. And then it starts from there. So the first thing it's going to do is it's going to look at this logical expression, and it's going to evaluate it again. And if that logical expression evaluates to true, then it's going to go again into the while loop, and it's going to again execute all the code in here, blah, 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 blah. It gets to the curly bracket, and yet again it goes back to the beginning. And again, it's going to check it. And if it's true, then it's going to keep going, and it's going to keep doing the same thing over and over again until when it comes back up once here, it evaluates this logical expression. And if this time around, this logical expression now evaluates to false, it's kind of like the if statement. If the logical expression in the if statement evaluated to false, then it skips it, right? It doesn't do the if statement. Well, same thing here. If the while loop logical expression evaluates to false, it does not go in. It just skips it until afterwards. So it's very much like an if statement, but with the one difference being that when it finishes running this the code inside the curly bracket, instead of just keeping going down, it goes back to the top. Okay, that's the big, tiny but big difference that makes the whole world. So everybody kind of got that, and of course we'll run some code in a second here to kind of practice. So we're actually going to try doing this with implementing the POW function. That's a good idea. I don't think that's the homework assignment. So yeah, we should be good there. Okay. So what else I want to say? There's nothing else to say about it though. In a second though, I will show you the do while loop. So hopefully I don't forget to do that one. It kind of works like the while loop, but there's one difference, and it's very not used because people, I don't know, they're scared of it, I suppose. Okay, so we got another program. This one's called loops. Right now nothing prints, perfect. Okay, so let's go ahead and write our first ever while loop. While, in this case, we're just going to put a 1 in there. That means true. What do you think is going to happen? I'm going to write in here LOL and end line. What do you think is going to happen in this program? Maybe you put a ready, set, go at the beginning. Ready, set, go. And at the end, I'm going to put a done. It's going to go forever. Yeah? Well, forever is a big word. At some point, I'm going to have to shut the computer down. So, I mean, if we have electricity and if, like, the machine can actually sustain functioning for eternity, which is a big if, because at some point, some parts are going to fail, which will make it shut off. It would otherwise run forever. And yes. Ready? I'm gonna press enter. Get ready. Oh, I can't show you the keyboard. I was gonna pull the keyboard and kind of show you me pushing it. But here I go. Bam. And as you can see, it's just printing LOL repeatedly. It's kind of flickering there. And yeah, it's just gonna go forever. It's looping. We achieved our task of looping. Of course, we want to control the beast here. You know, we kind of let it loose, and now it's going to take over the world unless we stop it. We can use, of course, that Control C to quickly stop it and save the world. In fact, let's use our Linux redirection and just kind of let it run. Okay, let's wait maybe 5 seconds. I think it's good. All right, let's take a look and see what this did, like how big of a file this made. It's called output.txt. So let's see. It made a 15 megabyte file. 15 megabyte file of just pure LOL. That's a lot of LOLs. We can use the more command to kind of look at them. You can see there, I'm holding space down. We're not even past the 0%. That's how many LOLs there are. In fact, there's a function in Linux to count the number of lines. Count lines in file, Linux. I think I know it. I think it's like W something. Yeah, WC, word count. And -L is the argument for the line number. So we can do word count -L, which is line numbers, again, commandline arguments. And then output.txt, it has a total of 3,800,000 approximately lines of LOL. Okay? So, yeah. It did that in what, like 5 seconds? Okay. Let me tell you just how big this can go. Kawa, or friendly student who also works with the admin stuff, found a file in Sally, I think, from a student that ran this something like this and just had a loop in there. And he ran it for who knows how long. He looks at the file. I think the file was about 1 terabyte. It could have been smaller, but I think it was about a terabyte. A 1 terabyte file that was called a.out. That was just the name of the file. He decided to call it a.out. What was in the file is one of the greatest mysteries that I will never find out, because they deleted the file before finding out. And I'm so angry at that, because I really wish I would have known, because that would actually kind of told us more about like how this happens, if it was a malicious thing or it was an accident. But no, he deleted it, or Jamie deleted it, or somebody deleted it before actually looking. I mean, I don't know about you, but I would have been curious to see like, what did this guy do? Now, you saw 5 seconds creating 13 megabytes. Extrapolate that data and figure out how quickly you can make those files go big. Unfortunately for you guys, you won't ever be able to do that again, because now they set some file limits. So I think if a file gets bigger than like 1 gigabyte, it just doesn't let you save the file and it throws it away or something, or your program crashes. They did some sort of safeguard to avoid it. But yeah, I think it was one of my students too. But again, they deleted the file so quickly that I will never find out. But yeah, it's a cool story. It's a real story. It happened last semester, I think, actually. I think it was last semester. It might have been in the fall, but I'm pretty sure it was in the spring. But yeah, I mean, if Kawa was here, he could tell you. But if not, ask him on Discord. Ask Kawa on Discord, and he remembers this. It's hilarious. I mean, you know, then they're blaming me. They're like, why are you making your students make such big files? And I'm like, no, I didn't do that. I never told them to make a 1 terabyte file called a.out. But yeah, so beware though, because while you can't do it on the server, you can definitely do that in your Linux VM. And you can very quickly run out of space in your VM because you have some massive file. So with great power comes great responsibility. And that is the power that you have with a while loop. You can make your own version of big data by just running a loop for a long time. So yeah, that's kind of a little side story there. That's kind of interesting. And now has been recorded for eternity on YouTube. So yeah, because I think Twitch deletes videos after 2 weeks. So yeah, at least that's why it's on YouTube. So it's for perpetuity. When you guys all work at Google and all the big companies and CS developers, you can look back and laugh at the videos that I made and be like, you know, back in the day when I was so scared because I discovered a loop, and now that's child's play. So yeah, all right. So anyways. Okay, so we, of course, you know, we don't want to have an infinite loop. So technically, this is correct syntactically, but semantically, unless that's what we were going for, which is highly, highly doubtful, that's probably not what we want to do. So we want a way to tame the monster here by having a way to terminate the loop, right? And so, you know, we can go ahead and maybe this is kind of ghetto. But let's go ahead and create a file that has a bunch of numbers in it, and then we can terminate when it reaches a number. That could be, that's not exciting. Let's just make it terminate after 5 times. Yeah, let's just do that. Yeah, that's fine. There's tons of things you could do here. So we're going to create a little number called 5, n equals 5, and then we're going to want to create a variable called count equals 0. And in our loop, we're going to make count increase by 1 every time, so we can use a little plus, by the way, for that. Although, you know, this might be a good time to show you something cool. I didn't show you this when I was showing you operators because there was no need, but it's a shortcut. So notice that if I do something like count equals count plus 1, what this does is it takes the old value of count, adds 1 to it, and then saves it again. So in this case, it's essentially doing a counter. I could also use this sort of method, the post increment, or I could use pre-increment in this case because it's not going to make a difference because I'm not assigning it to anything. But I could do that. But another cool little feature that you can do in C++ is you can do this shorthand for this. I'll leave it there. So a shorthand for doing that, so adding the same variable plus something or subtraction or whatever, is you can do count plus equals 1. That means take count and add 1 to it and then save it on yourself. And this same logic works for any operator. Division, multiplication, and subtraction. They all work like that. And that's how they work. And it's just shorthand for doing this. Of course, you know, you switch this to a minus for the minus and the division for division or multiplication for the multiplication, okay? And of course, the advantage being that this could be any number, right? It doesn't have to be 1. But yeah, so well, let's go ahead and keep that +1 like that there, so because you've never seen it used. And it's just a nice little shorthand for when you're writing, because it's a very popular thing to update your own variables by taking the old value and doing something to it. So it's so popular that they decided to actually make it into a program. So not into a program, into a command. So yeah, okay. So right now we are saying that every time it runs, it's going to increase. In fact, maybe let's let it loop forever, but instead of printing out LOL, we're also going to print out the count. So you can kind of see that grow. Ah, crap. I ran it again. How big did it get for those few seconds that it ran? 2.7 megabytes. I'm deleting it just because I don't want to run out of space here. But G++ loops. All right, so you can see there it's running and the number keeps increasing. It's not going fast enough to show you overflow. But yeah, let's leave it running in the background. Why not? I can actually see my computer, like the CPU, like the fan turn on for some reason. I shouldn't. It's not that big of a complicated operation. But eventually, it's going too slow. I want to show you buffer overflow. So why don't we, instead of adding 1 to it, let's add 100. I want to show you something kind of cool here. There we go. And then it's going fast. I think it's about 1 billion now. It's about 1.6 billion, 1.7, 1.8, 1.9, 2, 2.1, 2.2. Ah, darn, it's not 1 billion, it's million right now. So it's about 300 million. So let's just let that run on the side here. While I talk about something else, what can I talk about? Well, okay, let's update the code. So here, I'll put that here like this, and maybe I'll scroll down so we can keep track of it. So I'll show you something that happens in a while. But anyways, of course, we don't want this to run forever. So what we're going to do is we're going to switch this. We'll leave it at 100. Why not? But let's actually make it stop when it reaches a number that's greater than 4,999. Okay? So we can say while count is less than n, so that while the count is less than what you want to reach, it's going to keep going. However, when the count is higher than this, then it's going to stop. Okay? And so that's what we're going to do, and that's going to be our event that stops it. Basically, once it has printed over this, of course, it should print out 4,900 because it's going by hundreds, and then it will never print out 5,000 because by then it will have. Oh, actually, no. I think it will print. Yeah, it will print 5,000. Actually, that'll be the last number that it'll print. Because here's the thing: it'll increase it to 5,000. It'll print 5,000. It'll print LOL, and then it'll check if 5,000 is less than 499, at which will say, yeah, it is. It's greater than. So it'll say false, and then it's going to come out. But it will definitely print 5,000, and by the same logic, it's never going to print 0, because even though you started at 0, you add 100 to it and then you print it the first time. So it's not going to print 0, it's going to print 100, and the last number is going to print as 5,000. We'll get to see that in a while. How's this doing right now? We just, so we got 3 digits there. It's kind of flickering, so it's kind of hard to keep track of. Yeah, so we're about 1.5 billion. I wanted to get to about 2.1 billion because remember what I was talking about with integers? The biggest integer you can have is 2.1 billion, right? You can't have an integer bigger than that. Otherwise, we get what's known as an overflow. And something kind of cool is going to happen when you get to that overflow. So it's getting close now. It's getting to 1.8 billion right now. Probably in like less than a minute, we'll be hitting that 2.1 billion. Now, I could have made this counter go faster by, instead of going by 100, maybe go by 1,000 or 10,000, and that would have gone way, way faster. But I've kind of committed now, so I kind of want to just get there. All right, it's getting close now. We're at 2 billion. We're at 2.1 billion and 4.7. We might have to go to our... Oh, there we go. It did it. Oh, I wasn't even looking. I'm going to stop the program. Guess what? Look at this. Look at this right here. We got a negative number now. What happened? Now, it became a negative number. It was going as a positive number, and I wish I would have stopped it right before so you could see that. But all of a sudden, not only did it become a negative number, but it started counting down. See? It went from that big number, 2.1 billion, and it started counting down from negative 2.1 billion, and it's counting down. You can see that they're going down by 100. And we can see it a little bit better if I go and do something like, we'll do by 100,000 each time and run it again. Oh, but I gotta get rid of the, if I wanna do that, then I gotta comment out this again. So we'll do it like that. That's going so fast. Bring that back. Okay, so let's go ahead and see. Nope, it is going so fast that I can't even stop it. So we'll do more numbers like that. Okay, so here we go. So you can see here that I got about to 2.1 billion and then it went back to negative 2.1 billion. Okay? So this is the overflow. What happens in the binary for this is it gets to the point where it's 0, 1, 1, 1, 1, 1, 1, and there's 31 of these ones in here. And the next number in binary would make this a 1 and the rest of them zeros. Okay? And then from there, the next number would be 100001. Okay? Well, it turns out that that stands for very big negative number. And so this is what is known as integer overflow, because when you make that last digit 1 by increasing it, it actually flips the value into being a very big negative number. And so that's why it starts counting down. And it actually would count all the way down and then all the way back up, and it would just kind of roller coaster its way around, which you can kind of see here if we go all the way here. So oh, let me switch it so you can see it. You can kind of see it here, do that. It's 1 billion right there, 1.3 billion. Ah, oh, this is annoying. Okay, 2.1 billion, and then we get to the negative numbers. Now it's counting down. So 1.7. And then it gets all the way down to negative 300, negative 3 million. And then it goes to positive 6 million. So you can see it's roller coasting back and forth. Very dangerous thing. You don't want that to happen intentionally. So yeah, that's just my an example. It's an educational experience to do that, I suppose. So anyways, of course, we are not trying to break the computer here. So what we're trying to do is make it stop once it gets over 5,000. How big is the file? Well, in this case, I wasn't saving it to a file. I was just printing it out to the screen so that I could see it. Had I saved it to the file, if it was printing every single digit, then there will be about 2.1 billion lines, right? However, I was going by 100, so then it would be about 2.1 line divided would be about 200 million, 20 million, so about 20 million lines. And then if each line has, let's say, 10 characters, that would be 10 bytes. And then 10 bytes would be times, how many did I say? Did I say 20 million? So that'll be about 200 megabyte file, I think. That would have been the size of it if I'd let it run, I think. 200 megabyte or 2 gigabyte, I don't know. My math is a little bit off. We can use C++ to figure that math out, actually. But yeah, anyways, it's not as big as you think it is, basically. Which goes to show that the guy that did the 1 terabyte file, yeah. But anyways, so in this case, we're going to make it stop before it gets to 5,000, right? So let's go ahead and save this. Yeah, it's saved. Let me scroll this up so you can see the full code. There we go. Okay. Oh, well, it went really fast because this number's too big. So let's go ahead and bring this down to 100 per step. There we go. As you can see, it just finished, even though it printed a lot, because it printed so quickly that it just kind of went all at once. So you can see here, it printed 100, 200, 300, and so on until 5,000, and then it stopped. That's because when it got around to that 5,000 mark, it looked at this line, 5,000 is not less than 4,999, therefore it did not go in another time, and then it went right to done. So there is your while loop, basically. Any questions on the while loops? By the way, something to note. Let's say that you are declaring a variable inside the while loop. And then you're doing a++. And then you do cout a. Let's say you run this again. Did I cout a? Maybe end line afterwards. You see it a little bit better. Notice that it's 50 here, 49, 48, 47, 46, and so on. This is kind of weird and very kind of sketchy. Because here's the thing. When you're running code and you're running it in that scope, it's very dangerous to assume that every time it runs, it's a brand new scope. Because here's the thing. The way I see this is every time this runs, I'm declaring a variable a. And I would assume that each time you declare it, it would ignore the previous one because it's gone at the end of the scope. But it's not. It kept it, actually. And you're kind of using a counter inside. And it's a working counter. This does not work in a lot of languages. Don't do that. It's a very, very dangerous thing to do. Do not do that. If you want to deal with something like a counter, you're way better off declaring it outside of your loop and then handling it that way. Like that. Much better, much safer. Weird things can happen if you don't do that. In this case, it was working fine. I don't trust doing that. I highly recommend you don't do that. I highly recommend that you're only declaring variables inside your loop that are only used in that specific iteration of the loop. And by the word iteration, I mean that specific sort of round. So while it's going here, that's the only time you use it. And then when it comes back up and it goes again, you wouldn't have needed the old value. You're just using a brand new value. So it's kind of like a temporary variable that you're only using for that specific iteration, okay? If it's something that you want to keep as a running count, don't declare it inside the loop. Declare it outside. Avoid a lot of headaches because in other languages, this wouldn't have worked. This would have messed it up. In fact, one way that we could have messed it up, actually, because we never did even initialize it, so that's kind of bad, is if you did this. Now, every time, this should give me a 2. You can see it's always 2 because every time it's resetting itself. So the only time that this sort of approach of declaring a variable inside and using it works is doing this. But already doing this is very dangerous because you're not initializing your A. You never initialize A. You just hope for the best that the compiler initializes to 0 for you. So it's a very, very, very dangerous thing to do. Don't do that. Two things: initialize your variables always, and because you're going to be doing that, it's going to be impossible for you to both initialize and use a variable inside a loop. So unless you lose the value every time it goes back to the top. So because of that, I don't ever want to see this kind of thing in here. You want to just keep it outside. It's so much better. Oh, cancel. So yeah. Okay. So that's the little spiel about that. That you want to maintain this as its own little scope. And with scoping rules, it can affect code outside, but anything that you declare here cannot be accessed. So suppose that like this A, after the program is done, I can go ahead and print that and say, how many times did this loop? And I can say A there, and that should say 50, I think. 50, okay? However, if I was doing what I was doing before, which is kind of really, really bad, as I said, it's not going to compile. It's going to tell me that A doesn't exist, because it doesn't in this scope. Because remember, this is higher in the mountain, that's lower in the mountain. So if you're trying to keep track of some data that happened in the loop, such as how many iterations it did, keep the variable outside so that you can update it here, but you can access it here to find out what the final answer is. Okay? So that's going to be your while loop for you. What other very popular usage of the while loop you can do? You can do it for files, for reading files. So you can do something like, let's go ahead and create a file here. Do I have a random file somewhere that I could use? That's a kind of big file. Maybe we can use one of the, oh, well. No, I don't want to use the number one. I want something truly random. Let's go on the internet and find Wikipedia article for C++. And I'm just going to copy and paste a segment of it into this file called wiki C++. I can't spell that. Okay, and I'm just going to highlight and copy a segment of that. Obviously, it's going to copy it all messed up, but it's okay. For our sense and purposes, now we got ourselves a little file. Okay, and so now, one of the cool things that I can do is I can take advantage of the Linux redirection that I showed you guys earlier and use it to read the file and maybe do something to the file. So suppose that I want to count how many letter A's there are in the file. Yeah, that's a good one. We'll come back and do the exponent thing at a later time. So let's go ahead and actually, we have a counter, that's perfect. So we're going to count how many A's there are in the file, okay? Or actually, easier one. Let's count how many words there are in the file, okay? So remember we were doing that one WC command in Linux is word count. I was just using it earlier to test the number of lines. I, of course, did it like this, and then I did the file name. But if I just did it with that, so like let's say, let's do it so that we can compare and we get the right answer. So word count wiki.cpp.txt. It tells me that there are, what do these columns stand for? Dang it. I forgot. Word count, let's see, print new line, word, and byte count for each file. So that's what it is. Okay, so this is how many lines there are in the file, how many words there are in the file, and how many characters there are in the file. So that's what those stand for, okay? So as you can see, the help command is pretty useful. Help argument is very useful in any Linux file to do that kind of stuff. Okay, so let's remember that. Number of lines, number of words, number of characters. We're going to see if we can at least count the number of words. Okay, so how we're going to do it is we're going to keep a word count, because every time that this loops around, we're going to increase that word count by 1. And at the end of the program, we're going to say there were space let's say that's the number 55 words in the file, and then that's it, just in the file, period. Okay, so that's kind of be the goal of our program. So how can I feed the text? Now, one thing I could do is I could literally just put a big C in there and just copy and paste everything, but that's just a horrible thing to do. We can use Linux redirection to just redirect the file that we just created, the wiki.cpp.txt file. We can go ahead and redirect that to our program. The only thing that remains is, how do we make our program stop at the end of the file? There are many ways. The most popular and easy one that I can think of is cin. Cin allows you to read text, right? But another thing that it allows you to do is, in the case that you're using Linux redirection and it tries to cin and it reaches the end of the file and it can no longer access input when it's supposed to expect input, it actually errors out and returns a false flag. And that false flag can be detected by the while loop, so that it evaluates the false, the logical expression, and gets out of it. So I think all I have to do is just create a little temporary variable here, because I really don't care what I do with the text. I'm just going to read it into a string, just temporary, and then do that. Maybe we'll add something else into our program. Practice some if statements. Let's say that we find the word "da" spelled exactly like this. We can see out and say, found a "da." Okay. Let's just say that that's the case. I don't know if there's any "das" like that. I'm going to assume there are, because it's the most common word. So we'll see if that prints out at all. Okay. So yeah, that's it. We're gonna go ahead and run this, and assuming that I remember my stuff, then we should be okay. What was this called? Oops. Expected semicolon line 14. Yeah, here we go. We are indeed missing a semicolon there. A was not declaring the scope. Oh, we changed the name from A. It's now called word count. Okay, we're ready. Now we just got to use our Linux redirection to feed it the file. So the file was called wiki.cpp. So wiki, run it, and bam, it ran pretty fast. And it did find a couple of "das." As you can see, every one of those lines that you see there is a "da" that I found. We can actually, you can add a little cout variable here, or a counter. Let's just call it a "da count," decount. Plus equal, so we can practice using our plus equal. Let's go ahead and create a variable outside the loop, like good programmers that we are. Initialize it to 0, like a good programmer that we are. And then maybe also at the end of this, print out that as well. So cout there where, also I forgot to put a space here that I noticed. There were the count "das" in the file. Just to show you something, if there's more than 10, we're going to put an exclamation point at the end of that. If not, we're going to put a 0. How about that? Yeah, that's some good practice for some if statement practice. Yeah. So we're going to say file, but then we're going to put an if statement. If the count is greater than 10, cout, exclamation point, and then end line. Or actually the end line, no, because we can do that in its own line for both. Otherwise, cout a period, and then cout an end line for both of those. Okay, so what that's going to do is, if the count of "das" is greater than 10, it's going to put an exclamation point at the end of the sentence file. Otherwise, it's just going to put a period. Just the uses of "das", so you can kind of get used to it. Oh, I forgot to put in my input. So wiki. Okay. So there were 198, that's more than I thought, "das" in the file, and you can see an exclamation point because there's more than 10. There were also 4,562 words. Let's see how good we were. How much did the word count tell us again? Word count wiki. 4,562. So there we go. We got it. We got the exact amount that word count got. So look at that. We just made our own word count. Our get a word count program. So yeah, congratulations. Now let's go ahead just to see if the exclamation thing works. Let's make that 200. So if there's more than 200, it would put the exclamation point. Of course, there's 198, so it shouldn't. So we're about to find out. No exclamation point. So there you go. That also works. So now you can make cool programs like that. So yeah, there is an example of your event-based loop reading until it gets to the end of the file. And yet again, the way I do it is inside of the logical expression, I'm actually reading into the variable temp the next word. And that way, this little expression actually returns a value. And that value can be true or false. And it's false whenever this fails, when it cannot read anything else. And that happens when Linux redirection, when you get to the end of the file. That's why this actually stops. Otherwise, it would have read forever and keep going and just keep reading the last word over and over again, actually. So that's how this works. Another way to do this so this is the way that I do it, but there is another way. I have it written down here, and that is called end of file. I think it's like cn.eof. Well, it's not here, but I think it's just like this. So what we can do is we can move the reading of the actual text inside of here. But I think what you do here is you put .eof with parentheses, and I think that works. However, there's one issue with that. I think it's going to... oh no, it just died. It didn't do anything. Yep, so it didn't work. Don't know why. But hey, I don't use it, so there you go. The other one that you can do is like this. You can keep the cin on its own like that, because what's going to happen is the cin will set itself to fail after this. The issue with doing this is I think it's going to go one extra time. Yeah, see that? It was supposed to be 462. That's what word count gave us. But here it goes one extra time. The reason why is because this reads in let's say the last word. What is the last word, actually? Let's do tail wiki cpp. The last word is ill-formed, okay? And so that last word, and we can actually print it out here by saying temp cout last word tmp endline. Ill-formed. See, that's the last word that you read. But here's the problem of doing it this way. When you do this, it's reading in the word, what's the second to last word, I suppose? It's reading, let's say it's reading function. It reads function, goes around, reads the word is, right here, goes around, then reads the word ill-formed here, increases the count, but it goes around one more time. Because only when it gets to this line again, and then it's like, oh, there's nothing else to read, then it fails. So then this doesn't do anything. But see, the word count still goes up by 1. And it still does this whole piece of code. And only when it gets around to the top, then it sees that it failed and it gets out. So that's why you're getting that extra count this way, which is why I don't like it. And I like my method, because my method, by putting it on inside of here like this, avoids that problem because it's doing two things at once. It's both reading in the file, the next word in the file, but also in the same line, if at this time it fails, then it will kick you out. And at least in this scenario, it'll do this. And it can and the reading in still goes ahead and keeps the last word in temp. So you still have that word. So that's why I like this method. But anyways, both work depending on what you're trying to do. Just beware of that being off by 1 situation. Okay? What is the other one? That cn.eof. I was almost sure that that's how that one works. I don't really use it, but I see a bunch of students use it in 202, so I'm assuming somebody teaches them this method. I guess it just doesn't work for Linux redirection, maybe. That could be it, actually. Yeah, it might not work for Linux redirection, maybe just for file streams. So do know that this is another method if you see it. However, in my class, you know, obviously you're gonna do it my way because I'm the teacher, so I'm biased. So that's what I like because it works for what I do, and I'm happy. You know, if something is good, why mess it up? So let's see, what else do I want to say about that? I think that's it. Some basic. By the way, this is in the book, chapter 7, I think. Oh wait, no, chapter 6. This is chapter 6 in the book. Infinite loop, by the way, is basically when it loops forever. We already talked about that. Are we ready to talk about a for loop? Let me show you the do while loop first. Yeah, and then we'll talk about the for loop. So let's go ahead and add some code down here after we run our normal code. And this time I kind of want to leave this because it's pretty cool. Let's go ahead and do the one with the exponent. So let's first just do it with the while loop as more practice. So our goal is we're going to ask the user, well, we can't really ask him because we haven't been reading from a file. So we'll just hard code it for now. So we'll hard code two variables, base to for and exp to exponent, and that one is going to be 3. So 4 to the third power, which should be 4 times 4 times 4. Okay. What is that equal to? Well, 16, that would be, I think, 64. So, yeah. Okay. So the way we're going to do this is we are going to, what we can do is, yeah, we'll do it this way. While exponent is greater than 0. Yeah, we'll do it this way. And then what we'll do is we're going to take base. Oh, yeah. Let me scroll down a little bit more. There we go. Yeah, so we're going to have base, exponent, and then we're going to say, well, exponent is greater than 0. We can go ahead and say base is going to get base times itself. Yeah. Yeah, base equals base times base. Yeah. No, but then we will give that value down. So I guess in that case, we'll need to keep a int answer. Yeah, okay, we'll have to do it like that. So we'll keep a variable called answer, which is going to start out with a 1, because if we start out with a 0, the thing will not work. And so what we're going to do is we're going to multiply that times the base of the problem that we have, the base and the exponent. We're going to multiply it times the base every single time, and the number of times we're going to do it is the number that's an exponent. Okay. The reason I have 1 is because if I do 0, then it's 0 times whatever is still going to be 0, so you'll always end up with 0. That's a bug. So yeah, okay. And then we're gonna, every time that we do this, we're going to decrease the value of exponent. So the first time is going to be 3, then 2, then 1, and then 0. So I think this will work. If not, we can switch this to be greater than or equal to. But I think we should be good. So let's go ahead and see out. The answer is, and then answer, and then end line, okay? And it's still going to do the whole reading of the file, but whatever. The answer is 64. It worked. So as you can see, it's a not routine way of doing that, I suppose, because we're modifying the exponent, but that's okay. We're basically saying decrease the exponent every single time, and the moment it gets to a 0, then it stops. So it's going to basically run this 3 times, which each time will do 4 times whatever. So the first time it's going to do 4 times 4, or sorry, the first time it's going to do 1 times 4. The second time it's going to do 4 times 4. The third time is going to do 16 times 4, which will give you 64. We could change this. Let's do 5 times 3, or 5 to the third power. 125. Let's do 5 to the 4th power. Should give me 625. There we go. Let's do 5 to the 5th power. Of course, you could do this with interactive input, but in this case, I'm not. 3125. and so on. Let's go ahead and do 2 to the 32nd power, which is the size, the biggest number that you can have in an integer. We get a 0. Why did we get a 0 there? That's a good one. That's a very, very good one. That's because we overflowed, probably. We probably overflowed there. And so we need to keep this in the bigger number. So we can actually, instead of using a int, let's use a long for that. And there you go. Now we can keep that big number there. So yeah, that's actually twice the size of the biggest one you can get. I guess the biggest one you can get is actually 2 to the 31st, because it keeps about positive and negative. So yeah, we get 2.1 billion. And so there you go. Any questions, by the way? Got 20 minutes left. Okay, so no questions, I guess. Or if they come, I'll answer them when they come. So now I'm going to do the same thing I did here, but I'm going to use something known as a do-while loop. Okay? So a do-while loop works very similar to a while loop. In fact, it's so weird that I actually have to write it down to make sure that I remember the syntax of it. I think this is the syntax. Let me just compile and make sure. Yeah, okay, we're good. So do-while loop works just like a while loop with one exception. With a while loop, the checking, the logical expression checking, is done at the beginning. So it's very possible. So like, for example, if here I was to say 2 to the 0 power, which is 0, you know, if I was to do that, it would tell me the answer is 1. That's kind of scary, because what is 2 to the 0? Let's see, 2 to the 0, Google, tell us. 1. Okay, that actually works out for our scenario. But what if we wanted it to be 0 for some reason? This wouldn't really work because it never goes into the loop, right? So it would never go into the loop. So there are scenarios where you want your code to run at least one time in the loop, at least once, and then it can check. So right now we're doing the check at the top of the loop. So before we run the loop code, we check if we're supposed to, and then we go in. The other way around is we could run the code, kind of YOLO it, and then at the end of it, check. And if at that point we say we're not supposed to go in, then we just get out. But that, because the check is at the bottom, it means we are guaranteeing that you will at least run one time the code inside the loop, which may be useful for scenarios, you know, depending on what you're trying to do. You know, there's scenarios, but it's not used as often because people, I guess, don't really practice with it, so they don't feel comfortable using it. You can mimic the same thing in your code by making this be an infinite loop, and then at the end of this using a break statement. But I'll talk about break statements next time, actually. So anyways, for now, I don't know what happened there. Weird things came out. There we go. Okay. So let's go ahead and show you how to do the same problem using a do-while loop. You're still going to have the exact same stuff, except here we're going to have another answer. So we'll call it int another answer. And then we'll set that one to 0. Or here, we'll do completely different stuff. Yeah, we'll just do the same. We'll move this after the answer is part, so we can reuse the same variables. Except we gotta reset them. So we'll set it to 0. The base actually doesn't need to be changed. That can stay the same. But the one we gotta reset is the exponent. So this is not as exciting though. Let's go back to doing 2 to the 31st power. So exponent we need to reset back to 31. And answer we gotta reset back to 1. Okay, so from now we can still have the same code inside, like that, and we can still have the same check. If exponent is greater than 0, we stop. Okay, and then of course have we'll call it the other answer is answer 1. What am I trying to do? Oh, equal 1. That's what I'm trying to do here. Okay, so we got the same answer for both, right? If you want to make it look pretty, we can use IO manip, or I can just kind of space it out. Makes it easier to compare the numbers, right? Okay, so we get the same answer because it's technically doing the same thing in this situation, because you're going in, you're doing the first sort of multiplication, then you're checking if you're done, and if not, you keep doing it. So the while loop and the do while loop do the same thing after the first pass, as long as the first passive value is true. It's only going to change in a situation where you're not supposed to ever go in. So like the case of 2 to the 0. So in 2 to the 0, as somebody said, you're supposed to get 1, right? And you do with the first one, with the first loop that we did. But with the other one, you get a 2. And so that's kind of weird. Why do you get a 2 instead of a 1? Well, because in here, as correctly done, it checks whether the exponent is greater than 0. It's not, so then it doesn't do any operations to the number. It just keeps the 1. On this one, however, the do while loop guarantees that you're going to go into the code at least once, which means you basically run the code. So you take 1 and you multiply times the base, which is 2. And then you decrease the exponent from 0 to -1, which after then you check if -1 is greater than 0. It's not, so you get out of the loop. But you did the multiplication, whereas here you wouldn't have done it. And that's why you end up with a 2. So of course, in this special scenario, you don't want to use a do while loop, because that's going to cause an error in your code in the special scenario of 2 to the 0. In any other value, as long as it's not an exponent of 0 here, as long as it's a positive exponent, then it's gonna give you the right answer. So if I do something like 2 to the 3rd power, which should be 8, both of these are gonna give us, oh, I forgot to reset it over here as well. 3. Both of these are gonna give us 8. Okay, so like it works perfectly the same as a normal while loop. Only in a situation where you wouldn't have entered the loop in the first place does there make a difference. And that's why some people don't like to use the do while loop, because most situations you're okay doing this, and this may confuse some people. So it's good to know though, because if you see code with a do while loop, you know the very big important difference of it. So if there's an error, if you're working in a company and somebody uses a do while loop and the code is wrong, and you're looking at it and you see a do while loop and you're like, oh, well, that's why you're not supposed to run into this code here. You're supposed to check before, then you could detect that as the error, right? So you need to know what they are, even if you don't necessarily use them, so that you can potentially find errors in other people's code. Or you can better read code if you're reading code and you understand how that works. So that's the only difference between a while loop and a do while loop. Syntactically, notice that do is indeed a reserved keyword in C++. And also, you have to put a semicolon here at the end of this, whereas with the normal while loop, there's no semicolon in the curly brackets. Here there are. That's just part of the syntax of C++ and why it's done that way. You do put the word while and you still put your logical expression, but that semicolon sort of indicates the ending of that do while loop block. Okay? So that is a do while loop. It's also an event control loop. And so that's looping for you. I haven't shown you the for loop yet, and I'm not going to do that today because we're running out of time. I'll do that next class. But here's the thing. Any code that requires iterations or looping can be done using a while loop. You don't ever need to use a for loop in your life, because as I'll show you next time, you can write any code that requires a for loop, you can write using a while loop. And vice versa, by the way. You can write any code that requires a while loop using a for loop. The only reason you want to use one or the other is because it makes your code look nicer. It's just better. It's just a better and more elegant solution. The for loop is very popular. I'll tell you this. I personally find myself using a for loop far more often than I use a while loop. Like I'd say maybe 90-10 in terms of percentages. But the while loop is the most sort of OG of the loops. Like it's the first one that came out, I think, before the for loop. And it's the one that you should really understand. because then the for loop just makes more sense. The idea that this is how you get out of the loop, that you can use a counter out here to control the loop and figure out when it exits or not, which then you can use a counter-based loop using the while loop. But you can also do event-based, such as here when we were doing the cin, okay? So yeah, that's basically your while loop for you. And you know, even though we haven't really talked about functions or arrays yet, I think arrays are the last thing that you really need to be able to code just about anything. But even now, with a while loop, the world just completely opens to doing so many things, because while loops are a very critical part of your programs. I think both while loops and if statements are the most important parts of programming that you have to understand. And that you, more than understand, you have to familiarize yourself with them. And the only way that you can do that is by just practicing, writing tons of programs that have if statements and while loops on them. Okay, that's going to be kind of like the big thing that you should really do to familiarize yourself with them. So we got 10 minutes left. So instead of showing you the for loop, what I do want to show you, because I think I can cover it quickly and it's not something that is super important, but it's kind of good to cover, is I'm going to show you the switch statement. Okay, so let's go ahead and look for the switch statement. And that one is okay if we don't finish today, because I'd rather cut that one in half than the than the while loop. Okay, so I copied and pasted to save some time. That was my dog's fault. He made me erase the main function. There we go. Okay. Oh, it's like so hot because she was here. Now I feel like cold. Okay. So another way of using a sort of a branching thing like an if statement, there's this thing called the switch statement. And the switch statement is very, very useful when you find yourself writing a code and you got a bunch of if statements like one after the other. So like if you say something like, let's say that you're trying to detect what character something is. So remember we were talking about characters earlier. We're going to say car C has a 3 in it, okay? And we're trying to convert car C from a character into an actual integer, okay? And we're going to keep that into our int, n, okay? And so, of course, we could use the a to I function, but we're going to do it ourselves. Like, that's just so... In fact, yeah, we'll just do that. Okay. And so what we can do is we can use a switch statement like this, and we have cases on our switch statement that represent specific situations where it would evaluate to true. So normally, if we were doing this as an if statement, we could do something like if C is equal to 1, then n gets 1. Else if C is equal to 2, then you can say n gets 2. You could also just keep writing this as a bunch of if statements like this, because either way, it's never going to go into one or the other, right? Like, it's impossible for C to be both 1 and 2 at the same time. Okay? And you could just keep doing this, basically. In fact, I'm going to copy and paste to save some time here. Into 4, 5, 6, and so on. Okay, let's just say we're just going to 6, okay? Let's say we only expect to see the numbers 1 through 6. And then we can say C out n, and we can do math to it. So now let's say we're going to do n plus 1, okay? So let me just go ahead and return 0 here, just so it ends the program there, so you can see it. G++ switch. Let's see if there's any errors. Oh, dang, we got so many errors. Probably because of the switch statement. Let me get rid of that. C was not declared the scope. Oh, equal sign. And we get a 4. So that's good. So that means that the 3 was indeed found and caught by this if statement, and then we were able to do math. if we try to do here actually C plus 1, I think that actually would work too. We'd, oh no, we do concatenation. That's weird. So we get 52. Oh yeah, we're getting the car equivalent of that. So in ASCII table, that would be a 51 probably for 1 and 52 for 2 or something like that. So yeah, we're getting some weird stuff, right? So that's why we want to convert it to an integer so that the math actually works fine, right? That's the A to I magic going on that we're doing by hand. Okay, so here's the thing. This is nasty. Just a bunch of if things like that. It's just like disgusting to look at. Like, you know, like people will just shake their head and be like, no, don't do that. The other solution, you know, modern problems require modern solutions, is you can use a switch statement. And so the switch statement is kind of like a bunch of if statements that you kind of squish down into this sort of special syntax. And what you can do is you can have cases in the switch statement, and what those cases do is they're kind of like the equivalent of saying if C is equal to 1, if C is equal to 2, and so on. And so the way you do that is you write the keyword switch, then you put your parentheses, you put the variable that you're going to be checking, and then you compare it to basically the literals that you would otherwise check. So you can do 1, 2, 3, and so on. So let me just go ahead and throw in all the way until maybe at least until, yeah, let's do until 6. Oh, now my dog is back. Just begging me to come up. But no, you left me. All right. So now, in each of these cases, you can go ahead and set n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5. I screwed up. I did not put this semicolon. N equal to 6, okay? But there's more to this than that. I was going to talk about this next time, and I will. But you have to add the keyword break. Because the way switch statements work is they sort of keep flowing beneath each of them. So for now, we'll talk about it more later. Just remember that you have to put this keyword break, okay? So we'll revisit the switch statement once we talk more about what break actually does. But if you do this, and then there's a thing called the default as well. The default case is like having an else clause at the end of all of this. That's like the if nothing else catches it, then you do this. In this case, I guess the default we're just gonna make n equal to 0, and that's gonna be your sign that like we don't know like what this number is, but it's definitely not anything from 1 to 6. Okay. In fact, we'll do -42 just for fun. Okay. And so if you do this, this will actually do the same thing. So if I go ahead and see out again n plus 1, I should hopefully, ideally, if I don't make a mistake here, I should get a 4 again. We got a bunch of errors. Oh, I see. I forgot to put a curly bracket for my switch statement. I do believe you need a semicolon after the switch statement. Okay, so now we got line 32. We're missing a colon here. Perfect. All right, do we need this semicolon? I think you do, but I want to double check. Nope, you don't. Okay. So no semicolon for it. And there you go. I got a 4 as well. So these two lines of code, or not line, but these two groups of code do the same thing. It's kind of the equivalent of doing a bunch of else ifs in here. More than just if for each of them. It's more of each else if. And then having at the bottom the else that would say n equals -42. We can see this by having, of course, here, like, let's put a car for it as a T, like a letter T, so it's not a number. Semicolons. -41. So it gave us -40. I guess I thought I put -42. Oh, plus 1. That's why. -42 plus 1 is -41. So, yeah, there's the default down there, which is the same thing here as the else right there. Okay? So basically, these two are now equivalent in the sense that here we have an if, else if, else if, else if, else, which is sort of our fallback or emergency situation. And then in the switch statement, we have switch C, case 1, 2, 3, 4, each of them setting it. And then at the bottom, we have, of course, our default. So yes, that is how the switch statement works. Again, we will revisit it more in detail once we learn about break, but I kind of wanted to introduce it because we had 10 minutes to spare, so why not introduce something else that also, again, isn't covered in a lot of classes in 135, so I want to make sure we cover everything as much as we can, actually. You can't ever cover everything. But yeah, any questions about the switch statement? Again, the default, you put the word default. These are all reserved words in C++. Default, break, switch, and case, they're all reserved words. And again, we will talk more about why you put these breaks later on. And again, you put curly brackets. And again, so basically, yeah, just look at these. C equal 1 is the same thing as saying C1. So it's just kind of, you just have to kind of see them back and forth until you get it. But yeah. That's pretty much it. That's pretty much the topic of the day. Again, next time we will go ahead and talk more about looping by talking about the for loop. I will talk about break and continue. Then we will revisit the switch statement, and I'll talk more about break in there and how that works once we talk about break and continue. And then if we have time, we will start talking about file streams, which will be the assignment after the next one. So yeah. That's it. It is 11 now. If there are no questions, then that is it. Make sure you get your assignment done. I do believe there is an assignment due tonight. So assignment 3, I think. So yeah, get that done. I should be awake at least until 3 p.m. After that, I don't know. I've been sleeping pretty early, and then I wake up really early. So yeah. Cool. All right. Well, thanks for being here, guys. If you redeem the extra credit, make sure you message me on Discord. I do see a couple of messages already there. I'll check them afterwards. When is the midterm again? I sent a message out on Canvas. So I don't know. I don't want to say a date that's wrong. Check that. And I did say that if you have any conflicts with that timing, then send me an email. I did receive one person that had a conflict with that time. And because of that, I'm going to extend the time availability of the test by a couple of hours. But yeah, if you don't let me know, then that's, it's going to get defined. And then that's it. So make sure you check that on Canvas. All right, then. If more questions, just hit me up on Discord. I do believe today the TA has office hours. So he's going to be on the Discord voice channel. And it's just going to be idling there. So that's the perfect time. If one of these concepts doesn't make sense and you need that one-on-one help, you can jump on Discord and just have a one-on-one discussion with him where he can help you out to understand any of the concepts that we covered or any of the issues that you might have with the homeworks. So definitely take advantage for that. So yes, and there will not be a study guide for the midterm. So yeah, it's just, I don't even know what I could put on that. I guess the study guide is basically the C++ manual. Because I mean, it's like, how does a while loop work? You just got to look at an example of a while loop, right? Like, what can I do? You can expect we'll have a sort of a quote unquote review session, but you can expect to code in the test basically. Like, imagine one of the homework assignments, I make you do it on the test, like on the spot. Code it in, just type it into your computer and send it in. That's pretty much what the test is going to be like. So, yep. All right then. I'll see you guys tomorrow. Bye.